Hello and welcome to another Exoplanet Modeling and Analysis Center tool tutorial video. Today we're going to be focusing on the Live Atmosphere of Planets Simulator, also known as LAPS. So go ahead and navigate to the EMAC website and scroll down to find the LAPS tool. Before we launch off into the website tool, we're going to go ahead and click on the About tab just to learn a little bit more about LAPS. LAPS is a live, one-dimensional, radiative convective version of the LMD global climate model. The LAPS provides an accelerated and interactive simulation of the climate of any terrestrial planet or exoplanet. The tool was initially designed for students to explore the boundaries of the classical habitable zone, defined as the range of orbital distances within which a planet can maintain liquid water on its surface. The LAPS model provides a hands-on experiment by showing how the surface and atmospheric temperatures, as well as the profile of water vapor, evolve through time. And with that, we're going to go ahead and just launch right into the tool. The tool opens up. As you can see on the left, we have the graphs that are going to be populated by the information that we see from the tool. The right side hosts the two different tables of initial parameters that we want to put in order to tell the model how to run. The website itself is a little bit off with the way that that's laid out. It seems like the input boxes have extended past the drawn areas, but they still work completely to interact with. So the main three parts, as I said, are the graphs, the input parameters, and the start, stop, reset buttons at the bottom here. So the initial parameters are the quantity of liquid water at the surface, which is the mean thickness of oceans. On Earth, it's equal to 3.5 kilometers. If you were to choose 0, that would mean the planet is totally dry. Oceanic coverage is exactly what it sounds like. It is the percentage of the surface that's covered in oceans. On Earth, it is covered in roughly 70% of water. Gravity is gravity at the surface of the planet. On Earth, it is equal to 9.81 meters per second squared, and that is also the default. All of the defaults are going to be regarding Earth minus the liquid water one. The surface pressure is 1 bar of pressure at the surface of the planet. Earth is equal to 1 bar. The flux experienced by the planet at 1 astronomical unit is going to be this input parameter. 1362 is what the Earth experiences on average from our sun, but you can alter that depending on what the planet needs. You can alter how far away the planet is from the sun. Earth is 1 astronomical unit, but as we know, that only applies to Earth, roughly. Eccentricity, you can input the eccentricity from 0 to 0.4. The period of orbit, Earth is 365 days, but you can change that anywhere from 5 all the way up to 1,000 days. The amount of CO2 in the atmosphere can be put in parts per million, or you can also do it in percentages. So you can see that if you scroll the bar, it changes from 400 ppm to 900, and then it changes to percentages on the right side, anywhere from 10 to 50 to 100%. And last but not least, you can actually select the star type from 6 preloaded types of stars, from Blackbody, TRAPPIST, Proxima, to the Sun, etc. So I'm going to go ahead and hit reset just to get all of our initial default values back, and we're going to go ahead and click start to see how the graphs populate. So as the title of this graph says, this is the surface temperature in Kelvin of the planet across an elapsed time in Earth days, and so that totally depends on the period of rotation. The orbit is an actual graph of the period of the planet's orbit. So as you can see, as we approach 180 days, we are almost halfway through our orbit, just as the Earth is halfway through its period. This vertical graph of water vapor profile shows the water vapor mixing ratio based on the altitude in kilometers, as well as a logarithmic unit of the water vapor mixing ratio. The temperature profile is another vertical graph dealing with, again, in altitude. So as the altitude drops, the temperature rises, and the temperature is also measured in Kelvin. And last but not least, the energy budget is going to be a graph of the energy experienced by this planet. So the red line, if you scroll over it, it'll tell you the day that you're looking at, the flux it's experiencing, and what type of radiation it is. So the red line is the incoming stellar radiation. The blue line is the outgoing thermal radiation, and the green line is the absorbed stellar radiation. And from these values, you're able to glean information about how the planet and sun interact. Now, the best part about this is that you can get a lot of different information out there. So if you wanted to look at a planet orbiting a sun like the TRAPPIST-1 star, changing the gravity down to a smaller planet, let's say around there, its ocean coverage is 0, the surface pressure is heavier, and the period of orbit is lower, eccentricity is a little higher, it's closer, and the flux it experiences is at 1 astronomical unit is less. And let's say it has a 10% CO2 in its atmosphere. And then we click start and see what populates for us. So as you can see, the energy budget looks incredibly different from what we saw with Earth. The green line is way above what the Earth's was. The Earth, nothing got above the 300 range, but we are experiencing a much different energy. The orbital period is a lot shorter, so you can see the circles completing. The surface temperature is climbing at a much steeper rate than it did with Earth. Earth kind of had leveled off. It was in equilibrium almost, but this is just climbing. And you can see how long it takes for this to level off. If you stick with the model, it will just continue to go. There is no limit to how long you let it run. Something that's interesting about this is you can see this certain pattern that is appearing, dealing with the orbit and the types of stars and the type of atmosphere, everything about that. It's very interesting. Go ahead and stop the model here. So this is a really, really cool tool that can give some insight into a lot of different exoplanets based on the initial parameters that we gather about them. Feel free to use the LAPS tool, and as always, make sure that you reference the creators in any kind of publications you make. Thanks a lot.